Okay, so let us start. This is a second use case we are presenting here, also supervised by Petra and together with Dennis and me this time only. And we have been working on the basal ganglia also to implement a TVB-Nest model involving more details of the basal ganglia. And why would we even do that? Because we want to go towards virtual deep brain stimulation and actually introduce some stimuli there that can hopefully give us some realistic response of the whole brain, and then can see and predict optimal targets for patients. So as you can see on the next slide,
okay, we have to see how to change slides in this case.
If you do slideshow.
Slideshow. Where is it?
Up there, animation, slideshow, review. Yes.
Okay, is there a next slide? But this will do them automatically.
Yeah, play from start you can do.
Okay,
oh,
but now
okay, I see. Yeah. Okay, let's do it like this. So the motivation for this is actually, yeah, great.
Okay,
just
so
yeah, the motivation for this is actually why would we use deep brain stimulation just in general. To give you an idea, we have in the state space of where the brain dynamics can be. This is a very simplified version of this. We have a diseased brain and a healthy target brain in our vision, and then we want to use actually TVB to go and move the dynamics from the diseased brain towards the healthy target brain. Probably targeting fMRI resting state correlation matrices and make them as close as possible from a diseased patient to a healthy one. That's just a general picture. And why would we use DBS and what are the challenges there? So it has been shown that you can actually, with the right placement of the DBS electrode, help patients, in this case here, Parkinson patients, help them to actually improve clinically and measured by clinical outcome measures. So it's a very useful thing to do, but as you can see on the lower picture here, when you place the electrode as a neurosurgeon and you afterwards using, for example, this toolbox lead DBS, trace back where was this electrode actually placed, then you can see many different placements for different patients. And that has been analyzed by our collaborators in the deep brain stimulation lab here at Charité. And the upper right picture actually shows that the red lines, they were actually positively correlated with clinical development. So when an electrode was placed close to a red line and activated one of those red fibers, it was good for the patient, but the blue fibers was bad. So the placement is very, very important, and it needs to be targeted in an optimal manner. And of course, this can possibly be done with TVB. This is the ultimate goal. Yes, next one, please. So what we need for that is, of course, a very good model of the basal ganglia that actually fits reality as close as possible. So here, there's one recently published by collaborators of us in Chemnitz, and they actually enhanced the general Itzkevich model by adding some GM per GGABA. So there are some conductances of the synapses. So they enhanced the Itzkevich model, and what they showed, they fitted the parameters of their model such that actually, as you can see here from the little matrices, the experiments and the simulation were very close together. Their experiments and simulation matrices look similar here for different patients and controls. These were again Parkinson patients. And actually what they have used is just a model for the basal ganglia, where they put as a cortex, they put two populations of neurons. One was excitatory and one was inhibitory. And of course, we want to replace that probably in the future. And what did they use? Yes, next slide. Is they used their own software called Anarchy, which is a short version of Artificial Neural Networks Architect, developed in Chemnitz by themselves. And it looks actually from the build-up, it looks similar as to Nest, but it has some features that could be interesting to us. Like it simulates both the spiking neural networks, but also you can simulate rate-coded neural networks. And also it has an equation-oriented mathematical description in there, so you just need to plug in your equations of the models that you want to simulate. So it makes it easy for you to, for example, enhance this Itzikevich model or use any other model with some more parameters in a very easy plug in and play mode. And it has an interface in Python, but the code generation is actually in C++, which makes it possible to have parallelized computing here. And there's a lot of other customization possible where I will not go into details now, but the link is here. If you're interested, just have a look and check it out. So what are we doing with it? Next slide. Yes, we want to again build our own multiscale model because they so far have a good model that fits the basal ganglia and fits resting state fMRI data. But we want to replace the cortex by TVB to have the activation from the cortex as realistic as possible again, to also what we need later if we want to do virtual DBS. Actually, we want to witness what is happening, for example, in the motor cortex after a stimulation, and how can we best target this area to make it better for the patient. So here is their model in the lower part, which we want to simulate in Anarchy itself, but also in NEST. So we try to rebuild it with NEST. And it involves all the region of the basal ganglia and the thalamus. And it's connected via inhibitory and excitatory connections. And easy part, we want to just plug it in to TVB NEST and see what happens. So I will give to Dennis, and he will explain to you how fast this progress and how easy it was so far.
Yes, unfortunately, not so fast as I expected. So for the moment, we are trying to get acquainted with the Anarchy code we got from our colleagues. And thanks to Andre, a colleague of ours, we have managed to run the code and get the results back. But unfortunately, in the meantime, I was enhancing the NEST Itzikevich model to make it similar to the one our colleagues use in Anarchy. And this is my face until yesterday, because I mean, on the right corner, I don't know if you can see my mouse point, because I had some bugs in this implementation of the NEST Itzikevich model, which stopped us from simulating until now. Because this is me in the morning or the whole morning today. And I think half an hour ago, I found the last bug, but I didn't have time to confirm that. So unfortunately, I cannot show you any simulations yet. But I think soon we will be able to validate the NEST model similarly to the previous talk. And then, then we will show you how to continue. So for the moment, we are trying to integrate this basal ganglia model that has been previously fitted to empirical control in patient data in TVB NEST. There is a notebook. You can see the link where you can see the current status of our progress. Yeah, and I think Jil will continue from this point on.
Yes, so just to give you an overview again of the future challenges that lie ahead, we want to validate, of course, this NEST model against Anarchy. So both only NEST implementation of the TVB NEST part against only Anarchy, but then also, of course, what's getting interesting there is the interface between the basal ganglia and TVB, and that's something new that hasn't been done before. So we really need to think hard about it, like how best to interface those two softwares and how to make it as realistic as possible again, so that we can actually have a model where we can also show it later on to neurosurgeons or neurologists, and they will say, okay, this makes sense. This is actually quite detailed on what is really going on in the brain. And we want to connect it to TVB and also to different TVB field mean field models. So we were thinking about reduced Wang-Wang, but also here your input is appreciated, and we need to think and just try out also some of them to see what kind of data could we best fit. And also, what about TVB Anarchy? So that's the next step that our colleague Andre is also working on at the moment. Interfacing those two softwares would also be ideal for us, so that we can really be sure we have a good working model of Anarchy. Luckily, they shared their code with us, and that we can also connected to DVB and just benchmark the two implementations. So do two different implementations of TVB multiscale models with each other. And last but not least is, of course, the important part. Why are we doing this? We want to validate it with actual empirical data from DTI and resting state fMRI. And we have data available thanks to collaborations with other labs that is of Parkinson patients and of controls. And we want to use this in the end, if everything is fitted, to introduce a stimulus that should actually mimic a DBS in the brain and see if we can link different patterns of that stimulus leading to different dynamics again, if we can link those to clinical characteristics of patients. So as the last point, I just want to thank all the collaborators. Yes, and especially Petra, the supervisor, and Andreas, our master student working on the project. Also the other labs of the movement disorders and neuromodulation section here at Charité. They are connected also now via the project Retune, which just had a kickoff meeting yesterday, which is all about retuning the brain and helping patients to get better via also these virtual environments. And of course, the HAMK Lab, which provided us with their code from Anarchy as based in Chemnitz. So as here we have some references again for you, also the link to the notebook. Next slide, maybe, just as the last point. Yes. So if you want to know more about this and where is this coming from, if this piqued your interest, just feel free to check out the notebook or approach us via email or later in the discussion when it's scheduled. Thanks.